Constant force is applied to a 2.75 kilogram cart for 4.8 seconds to stop it. If the cart was traveling 25 meters per second, what was the impulse? Remember, impulse is a change in momentum of the cart, and what was the average force? Well, what do we know? We know that a force is a change in momentum per time. We know that we have a time. We know we have a mass. We know we have an initial velocity. We actually have a final because we know that it was stopped. So we can think of this as m delta v over t, 2.75, 25, excuse me, 0 minus 25 over 4.8. So this gives us a force of about a negative 14.3 newtons. Now the negative in this case would imply that it's opposing the motion. So we actually found the average force before we found a change in momentum. Well, we could have found the change in momentum simply by recording the mass times the change in velocity. This really was a negative 68.8 Newton seconds. Now Newton's third law, which is oftentimes learned in middle school as for every action there's an equal and opposite reaction, is effectively discussing or showing that we have a consistency or a conservation of momentum. Momentum is conserved. Now that is in the absence of any external forces or anything like that. So according to a cannon foundry, a reproduction 12-pound Napoleon fires a 12.3-pound solid shot 1,619 yards at 5 degrees with a muzzle velocity of 1485 feet per second. If the cannon weighs 1,230 pounds, what is the recoil velocity of the cannon? Okay, so while we could convert all of these numbers to begin with, we don't really need to. We can go ahead and say that momentum is equal to mv, right? It is conserved. So that means that the momentum of the ball plus the momentum of the cannon has to equal, when they're sitting there at rest, nothing's moving, 0. Now looking at this, we know that the mass of the ball is 12.3 pound equivalent. We know that the speed is 1485. We know that the mass equivalent of the actual cannon is 100 times greater, and so we need to know its speed. Turns out that the speed is simply going to be 100 times less, 14.85 feet per second. Then all we need to do there is convert feet to meters. One meter is 1 foot is 0.3048 meters. So we're looking at about 4.53 meters per second for the recoil velocity. Again, ignoring any sort of frictional forces for the cannon. How well do the range values match the theoretical expectation? So now, if you know what that is in terms of meters per second, which is straightforward calculation. So VB, which is 1485 feet per second, times 3048 meters per foot. And in fact, it is just 100 times this, 453 meters per second at 5 degrees. So I'm going to leave this as an exercise to determine theoretical range. Kepler's laws of planetary motion. We have 3 laws. The first one, that planets move in ellipses. 2, equal area in equal time. 3, that the square of the ratio of the periods is equal to the cube of the ratio of the semi-major axes. The moon orbits the Earth with a period of 27.5 days. If the moon is 384,500 kilometers from the Earth, how far away is an object that orbits in 19 days? 27.5 over 19 squared equals 384,400 over S2 cubed. So we have 2.09 is equal to 5.68 times 10 to the 16th over S2 cubed. So the S2 cubed is going to be approximately 2.72 times 10 to the 16th. So that the object is about 3 times 10 to the 5th kilometers away. So in this case, it's about 300,000 kilometers, which is most of the distance to the moon. Newton's law of universal gravity. The force between any two objects of mass is equal to big G, which is the universal gravitational constant, mass of the first object times the mass of the second object, divided by the square of the distance between their centers.